Hi everyone, my name is Junjie, and this course is about differential equations. So during this course, I will cover three parts. The first part is the general differential equations. The second part is the first order differential equations. And the last part is the linear second order differential equation. In the second part, there are four types of first order differential equations, and I will also cover the solutions to them. And they are separable equations, linear equations, Bernoulli differential equations, and the fourth type of differential equations that we can use the substitution to solve them. For the references and books, most part of this course is from this website, the Post Online Math Notes. And I also use some content from this book, The Calculus, the ninth edition in the chapter 9. And this picture is the cover of this book. Okay, then let's start with the first part, the general differential equation. To solve a differential equation, we have to know what is a differential equation first. So we look at the definition first. A differential equation is any equation which contains derivatives, either ordinary derivatives or partial derivatives. So I assume you all know what is a derivative, so I will skip to explain what is derivatives. And there are two types of general differential equations based on the type of derivatives. The first one is the ordinary derivative equations, the ODE. So this type of equations contain only one independent variables. So we can read them in this form. For example, we look at this equation here. It is the ordinary differential equation because it only contains one independent variable, x. And it can also be written as this form. So basically, we just substitute the y prime prime to another type, and they're the same thing. It's from the derivatives. Well, it is the knowledge of the derivatives, so I assume you'll know about it. Okay, the other type is the partial differential equations, the PDE. So this type of equations contain two or more independent variables. For example, in this equation, there are two independent variables, the x and t. So u is a function with regard to x and t. Okay, then we have to know what is the order of a differential equation. The order of a differential equation is the largest derivative present in the differential equation. For examples, the first equation, the order is 1 because the largest derivative here is the y prime. And similarly, the second equation, the order is 2, and the third one here, the order is 4. And back to here, in this equation here, similarly, we can know that the order is 2 because the larger derivative here is the y prime prime. And here, similarly, the order is 2. Okay, then we talk about the linear differential equation. So any differential equation that can be written in this form is a linear differential equation. And for nonlinear differential equations, they cannot be written as this form. And the coefficients, so the coefficients here refer to the a0 to an here. So, and the gx, they can be zero or non-zero functions, constant or non-constant functions. linear or nonlinear functions. So whether a linear differential equation, so whether a differential equation is linear or not, it depends on the derivatives part, and is irrelevant to the coefficients and the gx. And for the solution, a solution to a differential equation on an interval alpha to beta is any function which satisfies the differential equation in question on the interval alpha to beta. For example, here, the 4x times 2y prime prime plus 12x y prime plus 3y equals to 0 for the interval x larger than 0. We have this many solutions, and there are infinite numbers of solutions actually. And we can just plug in these solutions to this equation. And if the left side equals to the right side, then they are the right solutions. Okay, then the initial conditions. Since there are infinite numbers of solutions, how do we know which one is the solution that we want? And in this case, we need the initial conditions. So initial conditions are a condition or a set of conditions on the solution that will allow us to determine which solution that we are after. Usually they are written in this form, so they will give you the value of y when x equals to x0, or the derivative of y when x equals to x0. And the number of initial conditions required will depend on the order of the differential equation. So if the order of the differential equation is 4, then if we have to determine the solution, then we will need 4 initial conditions. If the order is 2, then we need 2 initial conditions. And the IVP, initial value problem, a differential equation along with an appropriate number of initial conditions. So the appropriate number of initial conditions here, basically it is what I explained before here. And the interval of validity, the largest possible interval on which the solution is valid and contains x0. So only the IVP problem has a interval of validity. And the general solution, the most general form that the solution can take and doesn't take any initial conditions into account. So when there is only a differential equation and no initial conditions, then we will have a general solution. For example, here, this equation y prime equals to x plus 1. So the general solution is the y equals x squared plus x plus c, and c is the constant. So basically, c can be any number. And we plug the solution back to the equation here. So y prime equals to 2x plus 1. So the left side equals to the right side. So this is the right solution. And since the derivative of c, the number will be 0. So only the derivatives of the x squared plus x, in words, the 2x plus 1 is left. And the actual solution, the specific solution that not only satisfies the differential equation, but also satisfies the given initial condition. So that is the solution when the initial conditions are taken into account. For example, here, the same equation, but this time we have the initial condition that when x equals 0, the value of y is 2. So we still have the general solution first, and we plug in y0 equals 2 to the general solution, and then 2 equals to 0 plus c, so c equals 2. And then we plug c equals 2 to the general solution, and we will have the actual solution here, y equals to x squared plus x plus 2. So basically, we have to solve the value of the constant, and we will use the initial condition to solve that. Then the explicit solution and implicit solution. So for the explicit solution, any solution that is given in the form y equals to a function of x. So the left side will be y. And for example, we look at this differential equation, y prime equals to x divided by y, and the initial condition is when x equals -1, when x equals 2, y equals -1. We have the explicit solution, y equals to minus the square root of x squared minus 3. And on the contrary, the implicit solution, any solution that isn't in the explicit form. So with the same example, we have the implicit solution that y squared equals to x squared minus 3. So in the left side, it is not y, it's y squared. Then it is implicit solution. Okay, then the second part of this course, the first order differential equations. The first type is the separable equations. So any differential equations look like this form. They are considered the separable equations. Okay, the first, in the left side, the ny is a function of y, and dy divided by dx is the y prime, the derivative of y with respect to x. And in the right side, the mx is a function of x. So if if an equation can be rewritten into this form, we can also use this. We can also use this method to solve this type of differential equations. And then the first step is to integrate both sides with respect to x. So the second equation here. And the second step is to substitute y with u. So now the ny will be nu. And then we calculate the differential of u, and it will be the y prime times dx, and it's exactly the same with this term. So we substitute this term with du. So the left side will be the integration of nu times du. So after the substitution, we have the fourth equation here. And the left that we have to do is solve the integration on both sides. And then we will have the general solution of u equals to a function of x. And then we substitute u with y again. And then we have the general solution of y equals to a function of x. Okay, and after the mathematically correct way, we have the first equation here is just what we talked about before. But there's an easier way to remember how we get this equation. but it is not mathematically right, but it will help us to remember how we achieve this equation. So the first step is to separate the derivative, but note that mathematically we cannot do this. So from the second equation to the third equation here, we just move the dx to the right side, and then we integrate both sides, and we have the fourth equation, and it is exactly the same with the first equation. But still, remember, we can't write the third equation in the exams or in any other like standard test. Okay, then let's look at some examples. The first one, the y prime equals to 6y squared times cosine x. And the solution, the first step is always to transform the original equation into the standard form. So we move the function of y to the left side, and then we have this equation here. So this equation, and then we know that the ny is 1 divided by y squared, and mx is 6 cosine x. And the second step is to transform into the into this equation, and then we have to solve the integration on both sides, and then we will have the general solution. And note that don't forget the constancy. It is really important, and it is a common mistake that many of you will make. And so the left side will be minus 1 divided by y. It is the integration of 1 divided by y squared. And the right side will be 6 sine x and plus the constant. And this form will be the implicit solution because the left side is not y, and we should rewrite it as a explicit solution. So in the end, we have this solution here. Okay, we look at another example. The y prime equals to e to the power of minus y times 2x minus 4. And in this time, we have the initial condition. When x equals 5, y equals to 0. And when we look at the differential equations, we know that the order is 1 because the largest derivative is y prime. And the number of initial equations is 1, so we can have the actual solution in this problem. And for the IPP problem, remember to solve the interval of validity in the end. And the solution, similarly, we have to transform the original equation into the standard form. So basically, we move the function of y to the left side and the function of x to the right side. And then we just integrate on both sides and solve the integration, and then we will have the general solution. So this is the general solution. And after that, since this is an IVP problem, then we have to use the initial condition. So we plug the initial condition into the general solution. And then we will have the e to the power of 0 in the left side and 5 squared minus 4 times 5 plus c in the right side. And from this equation, we can solve the value of C. So after we solve the value of C, we can have the actual solution here. Y equals to ln of x squared minus 4x minus 4. And finally, we have to solve the interval of validity. So x squared minus 4x minus 4 is larger than 0. That is because the proper number of the ln will always be positive. And then after we solve this inequality, we have two possible intervals of validity. And they are these two. And then because the second interval contains x equals to 5, that is the value from the initial condition. So the interval of the validity is the second interval. Okay, then we look at the second type of first order differential equations. That is the linear equations. So usually it can be written in this form. Dy divided by dx plus a function of x times y equals to another function of x. In this equation, px and gx are continuous functions. Okay, there are several steps to solve this equation. The first step is to assume there exists a mu x, and that satisfies mu x times px equals to the derivative of mu. So this is the typo here. It's not ux, it's mu x. And then we multiply the original equation. So this equation by mu x. So we have this one. And then we can just substitute this part with a mu x. That is from the first step. And then we have the equation here. And the third step is to apply the product rule and substitute the left side. So the product rule, it is this part. So basically, the left side can be transformed into the derivative of the product of mu x times yx. So it will be this equation in the end. And then the fourth step is to integrate both sides and have the solution. So after the integration, the left side is easy. After the integration, it will be mu x times yx plus c. And still don't forget the constant here, the c. And then we cannot solve the right side right now because we don't know any information of the mu x and gx. But in the real questions, after we know the function of mu x and gx, we can solve the right side as well. Well, and after the calculation, we move the constancy to the right side and divide it by mu x on both sides. We can have the solution here. And you might be confused why the c here is still plus c here. It is because c can be any number. So even though in the first, when we move c to the right side, it will be minus c, but c can be positive and negative. So it doesn't matter if it's a positive or negative sign in the front of the c. And then the fifth step to determine the mu x. So from this condition, that is from the first step, we assume that we'll assume that mu x times px equals to the derivative of mu. And then we know that p equals to the derivative of mu divided by mu. So it is a derivative of the ln of mu. And then we integrate both sides. So the right side will be just ln of mu x, and the left side will be the integration of px. And the k is another constant from the integration of the of this part. And then we just have to calculate the mu x. It is e to the power of the integration of px plus k. And we just move the e to the power of k to the front. And we rename e to the power of k with k, because e to the power of k is always positive, and we rename that with k. Here k is another positive number. Okay, and then we have the solution, or the function of mu x, that is k times e to the power of the integration of px. And the last step is to plug the mu x into the y. That is from the fourth step. This one is from the fourth step, from here. And then after the calculation, we have the solution of y. It looks a bit complicated, but if you just calculate it by yourself, I think it is easy to remember. And if you remember the formula here, you can just solve this type of differential equations very quickly. And here the same logic, rename c divided by k with c, since k is a positive number and c can be any number. So we rename c divided by k with c. So the new c will be still any number. And then this is the final solution, the general solution. And well, it is easier to remember if you write in this way. So y equals to the derivative, y equals to the integration of mu times g plus c divided by mu, and mu is e to the power of the integration of p. Okay, then let's look at some examples. The first example, y prime equals to 2xy plus 2x times e to the power of x squared. So the first step is always to rewrite the original equation to the standard equation, standard form. So basically, we move the 2xy to the left side, and then we know that the minus 2x will be px, and gx will be 2x times x to e to the x squared. And we apply the formula that we have. So mu x here, it is e to the power of the integration of px. And we plug in the px here. The integration of minus 2x will be minus x squared, and then mu x will be e to the power of minus x squared. And then the general solution, we plug in the mu x and gx. And after the calculation, we have the general solution that y equals to here e to the power of x squared times x squared plus c. C still any number, it is a constant. Okay, another example. In this example, we have the initial condition, and still the order is 1 and the number of initial condition is also 1. So we can have the actual solution in the end. So the first step is always transform the original equation into the standard form that we have. So basically, we divide by t on both sides. And then we can have the pt equals to 2 divided by t. So this part. And gt is the right side. So this part. And then we have to apply the formulas. So the mu t is the e to the power of the integration of p. So it is t squared in the end. Well, I assume you all know how to solve the integration, so I will skip to explain it. And then the y still will apply the formula. And then in the end, we have the solution here. That is the general solution. And for the IVP problem, we have to plug in the initial condition to the general solution in the end to get the actual solution. So after the calculation, we have C equals to 1 divided by 12. And the actual solution will be this one. And for the IVP problem, we always have to find the interval of validity. So in this case, since t squared is in the denominator, so t cannot be 0. And in the initial condition, the t0 is 1. So the interval of validity should contain 1 here. So the interval of validity is from 0 to positive infinity. Okay, the third type of first order differential equations is Bernoulli differential equations. So it looks a bit similar to the linear equation, but in the linear equations, they don't have the yn in the right side. But since they are similar, actually after the some calculation, we can apply the formulas that we have from the linear equation. So still here, the px and qx are continuous function, and n is a real number. So n here is a real number. And there are, for the together solutions, first step is to divide by y to the power of n on both sides. And then we will have this equation. And then the second step is to substitute the y to the power of 1 minus n, so this part, with v. And the derivative of v here, it will be 1 minus n times 1 y to the power of minus n times y prime. Well, still, I assume you all know how to calculate the derivative, so I will skip to explain it. And then we just substitute the y, well, this part, because it is exactly the same with this part. So this part will become 1 divided by 1 minus m times v prime. That is from this equation. And then the left will be the same. Well, still here, we substitute the y to the power of 1 minus n with v. So we have the new equation, this one. And then the third step is to apply linear differential equation formula, because we look at this new equation, it is the same with the standard form of the linear equations. So we can apply the formula directly. And the fourth step is to substitute v with y to the power of 1 minus n and solve the solution of y. Okay, now let's look at some examples. The first one is y prime minus y plus 2 times x divided by y equals to 0. Okay, then we have to rewrite this original equation. We move the term 2 times x divided by y to the right, and we divide y to the power of minus 1 on both sides, and then we will have this new equation. And just apply the steps that we talked about before. We substitute the y squared, so this part, with v, and we calculate the derivative of v prime of v, and then we will have v prime equals to 2y times y prime, and we can substitute the y times y prime with v prime divided by 2. That is from this equation. And then we have the new equation, this one. And we can apply the linear equation formula now. From this equation, the px is minus 2 and the gx is minus 4x. And we calculate the mu x and the vx. Basically, just apply the formulas directly. And in the end, we substitute v with y squared, and then we will have the general solution, this one. Basically, that's it. And another example, we have the initial condition now. Still, the order is 1 and the number of initial conditions is 1. So we can solve the actual solution in this case. So still, we just apply the steps. The first step is divide by y to the power of 4, and then we have this equation. And then we substitute y to the power of minus 3 with v. And then we have calculate the v prime and substitute this part. And then we will have this new equation and apply the formulas px, gx. Since we have the px and gx now, then we can apply the formulas to get the mu x and the vx. This is the solution. And after that, we have to substitute v with y to the power of 3 again, and calculate the solution, general solution of y, and this one, but in this case, it is an implicit solution. And we plug in the initial condition, this condition when x equals to 0, y equals to minus 2, and we find the value of c, and then we plug the actual solution. And this is the explicit solution form. So for the interval of validity, well, for the interval of validity, this part cannot be 0 because it is the denominator, and but after the calculation, we know that this 5e to the power of minus x plus 4x minus 4 is always positive for all real numbers. So the interval of validity will be all numbers. And the last type is to use the method of substitutions. So the form, so the equation, if a equation looks like this form, y prime equals to a function of y divided by x, then we can apply this method. The first step is to substitute the y divided by x with b. So y will equal to v times x, and we calculate the derivative of y with respect to x. Oh, with respect to x, yes. And then we will have this equation. And then we just substitute y prime with the right side. And we have the new function here. And the y divided by x is substituted with v. And the second step is to apply the separable equation method. So the first type that we talked about before. And we just move the v to the right side. And then we just, move the function of v to the left side and move the function of x to the right side. And then we just integrate on both sides. Okay, then let's look at some examples. So here, y prime plus 4x squared plus y squared equals to 0. And the initial condition is when x equals 2, the y equals to minus 7. And x will be positive. So the first step is to divide x squared on both sides. And then we will have the function of y divided by x. And then we can apply the method of the substitutions. Basically, we substitute y divided by x with v. And then we substitute the y prime with v prime x plus b. That is from, well, that is the what we talked about before. And then we will have this new equation. And we move the function of v to the left side and the function of x to the right side. After that, we apply the method of the separable equations. We just integrate both sides and solve the integration. And then we will have the solution here. And then we substitute v with y divided by x. So the left side will be this one, and the right side will be this one. So basically, take both sides to the power of 4 in the first, and then substitute v with y divided by x. And then we will have the solution that y squared equals to c divided by x squared minus 2x squared. So here still the same logic, we rename c to the power 4 with c. And then we plug in the initial condition to solve the value of c. And then we have the actual solution. And this is the actual solution. And don't forget to find the interval of validity. So in this case, we know that this part will be positive, will be greater or equal to 0. So we have to solve this inequality. But from the condition here, we know that x will be positive. So x cannot be 0. And also from this term, since x is the denominator, so it cannot be 0. And then we will have the possible intervals, these two. But we know that x is positive, so the second interval is impossible. So the interval of validity is the first interval, so this one. Okay, let's go to the last part, the linear second-order differential equations. So first, we look at the definition. And the general form is this one. So the px, qx, rx, and gx are all the functions of x. And the constant coefficient form. So the px, qx, and rx are no longer functions. They are constants. And the homogeneous differential equations. So the gx will be 0. So the right side here is 0. And the non-homogeneous differential equations. So the gx will be non-zero. The principle of the superposition, if y1x and y2x are two solutions to a linear homogeneous differential equations, so basically this equation, then so is yx, and yx is c1 times y1 plus c2 times y2. And here c1 and c2 are two constants. They can be any number. And the yx is also the solution of the linear homogeneous differential equation. Okay, then the characteristic equation assume y equals to e to the power of rx is the solution of the second order differential equations. Then the first order derivative of y is r times e to the power of rx, and the second order derivative is r squared times e to the power of rx. So we plug in the y prime and y prime prime to the homogeneous differential equations here. And then we will have this equation. And we can move the e to the power of rx to here. And this equation can be rewrite as this equation. And to solve this equation, we know that e to the power of rx is always positive, so the solution is this term will be 0. So 8 times r squared plus br plus c is 0. And this equation is called the characteristic equation. And this equation is very important to solve the second order linear differential equations. For example, the y prime prime minus 4y equals to 0. Well, we can have two solutions. The y1x equals to e to the power of 2x. So the y prime will be e to the power of 2 times e to the power of 2x, and y prime prime will be 4 times e to the power of 2x. And when we plug in the y1x and the y prime prime back to the equation, the left side is 0 and the right side is also 0. And similar, when we plug in the y2x, the left side and right side will be 0. And when we apply the principle of the superposition, the yt equals to well, it's yx here. Well, it's a typo. Yx equals to c1 times e to the power of 2x. So basically c1 times y1 plus c2 times y2. It's also the solution. And it's easier to prove. You can just plug in the yt and calculate it. The left side will be the same with the right side. And they are also 0 in this case. And the characteristic equation, in this case, it is r to the power of 2 minus 4 equals to 0. So we solve this equation and we have r equals to plus minus 2. And same, we have two solutions. The first one is y1x equals to e to the power of 2x, and y2 equals to e to the power of minus 2x. And we can find that these two and this minus 2 are the solution of the characteristic equation. Well, we will talk about it more detailedly later. And yeah, for the characteristic equation, the roots will have 3 forms. The first form is that and 2 roots are real distinct roots, so R1 is different from the R2. And the second type is the complex roots. So we will have complex roots, lambda plus mu times I. And lambda is a real number. Mu is also a real number. And the third type is the double root. So the equation has 2 same roots. R1 equals to R2 equals to R. Well, in the first case, the characteristic equation has 2 real and distinct roots. And then the linear homogeneous differential equation, this equation has 2 solutions. And they are y1 equals to e to the power of r1x and e to the power of r2x. So basically the roots are connected with the solution to the differential equations. And we apply the principle of the superposition. Then the general solution is C1 times Y1 plus C2 times Y2. and it will be C1 times e to the power of y of R1x plus C2 times e to the power of R2x, and C1, C2 here are constants. Okay, let's look at some examples. The y prime prime minus 7y prime plus 10y equals to 0. And the first step is to write the characteristic equation. So here r squared minus 7r plus 10 equal to 0. And this equation will have two roots. The first one is 5 and the second one is 2. And in this case, the roots are real and distinct. So the general solution is y equals to C1 times e to the power of 5x plus C2 times e to the power of 2x. So basically, we just apply the formulas that we have. Okay, another example, and in this time we have the initial conditions. And we see that the order is 2 and the number of conditions are 2. So we can have the actual solution. The first step is to find a characteristic equation. So r squared plus 11 times r plus 24 equal to 0. And in this case, still two roots, real and distinct roots. So we solve this equation and we have r1 equals to minus 3 and r2 equals to minus 8. And apply the formulas, we have the general solution. Yx equals to C1 times e to the power of minus 3x plus C2 times e to the power of minus 8x. And since the initial condition contains the derivative of y, so we have to calculate the derivative of y. And after the calculation, we plug in the y0 equal to 0 and y prime 0 equal to minus 7. We plug in the initial conditions and we can solve the C1 and C2. And then we will have the actual solution. Just substitute the C1 and C2 with the numbers that we solved. Okay, the second type is the complex root. So if the equation has two complex roots, R1 equals to lambda plus minus mu times I, then the linear homogeneous differential equation has two complex solutions. Still, we just plug in the roots to here, and we will have two solutions. And then we apply the Euler's formula. So these two, e to the power of I times theta equals to cosine theta plus I times sine theta. And e to the power of minus I theta equals to cosine theta minus I sine theta. And then we just apply this formula to these two solutions. And then we will have these two. Basically, we just move the e to the power of lambda x to the front because this term equals to e to the power of lambda x times e to the power of mu I x. And then since the e to the power of mu I equals to cosine mu plus I sine mu x, so we will have this term in the end. And similarly, we have the y2. And we apply the principle of the superposition to get a real solution. So basically the px here equals to c1 times y1 plus c2 times y2, and in this case we just set c1 and c2 equals to equals to 1 divided by 2, and then after we plug in the y1x and y2x, we can calculate the px, and px will be e to the power of lambda x times cosine mu x. And similarly, for the qx, we set c1 and c2 equals to 1 divided by 2i and minus 1 divided by 2i. And then we will have qx equals to e to the power of lambda x times sine mu x. Well, these are just some calculations. And then we apply the principle of superposition again, and the general solution is y equal to c1 times px plus c2 times qx. And then we have the general solution. And in this step, we just want to cancel out the terms with complex numbers I. So after the cancellation, we have the real solutions. So basically the I is eliminated in these two solutions. And then we will have the general solution in this form. Okay, then let's look at some examples. The first one, y prime prime minus a y prime plus 17y. The first step is always to write the characteristic equation. So r squared minus a times r plus 17 equals to 0. And the two roots are 4 plus minus I, and they are complex roots. So the general solution, we can just apply the formula that we have before. So y equals to c1 times e to the power 4x times cosine x plus c2 times e to the power 4x times sine x. So the coefficient of x here is 1 because here it's 1. And e to the power 4x here is 4 because the lambda here is 4. And another example, also we have the initial conditions. And similarly, the order is 2 and the number of conditions are 2. So we can have the actual conditions. So the first step is always write down the characteristic equation. So here, r squared plus 16 times r equals to 0. Oh, and here's the typo. It should be 16. Because this is not y prime. So the coefficient of y prime will be a coefficient of r. So here should be 16, is not 16 times r. Okay, the two roots are plus minus 4 times I, and we have the general solution. Still, but actually here it should be e to the power of lambda x, but because here lambda will be 0, so e to the power of 0 will be 1. So we see that the e to the power of lambda x is cancel out. And here the coefficient of x is 4. That is because the mu is 4 here. So basically just apply the formulas. And well, because the initial conditions contains the y prime, so we have to calculate the y prime. And then we plug in the initial condition to solve the C1 and C2. And then we just substitute the C1 and C2 with the values that we solved, and then we will have the actual solution. And the third case is the double root. So if the equation has double roots, R1 equals to R2 equals to R, then the linear homogeneous differential equation has the solutions y1 equals to e to the power of rx, and y2x equals to the e to the power of rx, and y1 equals to y2. And then we apply the quadratic formula. So R12 equals to minus b divided by 2a. So one solution is px equals to e to the power of minus b divided by 2a times x. So basically here we just substitute r with this term. And another solution, we just assume qx equals to vx times e to the power of minus b divided by 2a times x. It's also a solution. So basically qx equals to px times bx. And then we plug in the q prime prime x and q prime x and qx into the differential equation. And then the vx after the calculation will be cx plus k, and the qx will be cx plus k times the px. Well, this is from the calculation. After we plug in these three functions into the differential equations. And we apply the principle of the superposition rule, and we have the general solution yx equals to c1 times px plus c2 times qx. And then we have this final general solution, c1 plus c2k plus c2 times cx times e to the power of minus b divided by 2a times x. But here c1 plus c2k is just a constant, so we can write it as c1 and c2 times c is another constant. It can be any number still, so we can rename it with c2. And the general solution will be yx equals to c1 plus c2x times e to the power of rx. And r, we can know that it is minus b divided by 2a. Then let's look at some examples. So the first step, the characteristic equation, r squared minus 6 times r plus 9 equals to 0. And the double root, the root is 3. So the general solution is yx equals to c1 plus c2x times e to the power of 3x. c1 and c2 are constants. And another example, we have two conditions, initial conditions this time. So the first, we write down the characteristic equation, r squared plus 14r plus 49 equals to 0. Well, I don't know if you know about how to write the characteristic equation, but for me, it is easy because just take the coefficients here and replace the y prime to r squared and y prime to r and y to 1. So we have the characteristic equation now. And in this case, still this equation has double root minus 7, and we have the general solution. Just apply the formula. And then, since there are two initial conditions and contain the value of the derivative of y, so we have to calculate the derivative of y. And we plug in the initial condition to solve the C1 and C2. And then we have the actual solution. Okay, the last part, the reduction of the order. So if an equation misses y and y prime, we can just integrate for 2 times. It's easy. The general solution will be the integration of the integration of fx plus c1x plus c2. So basically just integrate for 2 times. And c1, c2 are 2 constants still. And so in this case, in this equation, y is missing. So we substitute y prime with px. So y prime equals to p, and y prime prime equals to the derivative of p to x. So we substitute using these equations, and y prime prime will be dp divided by dx, and y prime will be p. And then we can solve this equation, and after that we just substitute the p with y prime again, and after the integration we can have the solution of y. Okay, the third type, when x is missing, so we substitute y prime with p. So y prime equals to p, and y prime prime equals to the derivative of p with respect to x. And we can rewrite as this form. And so we can have the, since here, the derivative of y is p, so we can rewrite as this form, p times dp divided by dy. So this is the derivative of p with respect to y. And then we substitute the y prime prime and y prime using these two equations, and then we will have this equation. And then still we can solve the solution of p, and then we substitute p with y prime again. And after the integration, we can have the solution. And then the non-homogeneous differential equation. So basically we have the gx in the right side. So the general solution is yx equals to ycx plus the capital Yx. So here the ycx is the general solution for the corresponding homogeneous differential equation. And yx is an actual solution for the non-homogeneous differential equation. So ycx is when gt equals to 0, the solution for it, and yx is the solution for the non-homogeneous differential equation. And here is still typo. It should be x and x here. Okay, and that's it. That's the end of this course. Thank you.